In today's interconnected world, software is the backbone of our digital lives. From online banking to social media, we rely on applications for countless tasks. But this reliance comes with a risk: software vulnerabilities. These weaknesses in code can be exploited by malicious actors, leading to data breaches, financial losses, and reputational damage. Software vulnerability testing is essential to identify and fix these weaknesses before they can be exploited. It's like a routine health checkup for your applications, ensuring they are robust and resilient against attacks. The consequences of neglecting vulnerability testing can be severe. Cyber attacks are becoming increasingly sophisticated, and businesses that fail to prioritize security leave themselves vulnerable to devastating consequences. In this essay, we will delve into the world of software vulnerability testing, exploring its importance, methodologies, and emerging trends. Imagine a medieval fortress, its towering walls protecting valuable treasures within. But what if a single, overlooked crack in the wall allowed invaders to infiltrate the stronghold? Software vulnerabilities are like these cracks. They are flaws or weaknesses in software code that can be exploited by attackers to gain unauthorized access, steal data, or disrupt services. Just like a single crack can compromise an entire fortress, a single vulnerability can undermine the security of an entire application. These vulnerabilities can arise from various sources, including coding errors, design flaws, or inadequate security practices during the software development process. They can manifest in different ways, from allowing attackers to bypass authentication mechanisms to enabling them to inject malicious code into a system. Understanding the nature of software vulnerabilities is the first step towards building more secure applications. By recognizing the potential weaknesses in our code, we can take proactive steps to mitigate risks and protect our systems from attack. Software vulnerabilities come in many forms, each posing a unique threat to application security. Let's examine some of the most common types. Injection flaws. These vulnerabilities occur when an application fails to properly validate user input, allowing attackers to inject malicious code into the system. SQL injection is a classic example, where attackers can manipulate database queries to gain unauthorized access or modify data. Broken authentication. Authentication mechanisms are crucial for verifying user identities and controlling access to sensitive information. Broken authentication vulnerabilities can allow attackers to bypass these mechanisms, gaining unauthorized access to accounts or systems. Cross-site scripting, XSS. XSS vulnerabilities arise when an application fails to sanitize user input, allowing attackers to inject malicious scripts into web pages viewed by other users. This can lead to the theft of cookies, session hijacking, or the spread of malware. Security misconfiguration. Often overlooked, security misconfigurations can leave applications vulnerable to attack. This can include using default passwords, leaving unnecessary services running, or failing to properly configure security settings. Sensitive data. Exposure. Protecting sensitive data is paramount. Vulnerabilities in this category can allow attackers to access confidential information such as credit card numbers, passwords, or personal data. Understanding these common types of vulnerabilities is crucial for developers and security professionals alike. By recognizing the patterns and characteristics of these flaws, we can better identify and mitigate them during the software development lifecycle. Just as a doctor uses various tools and techniques to diagnose and treat illnesses, security professionals rely on different approaches to uncover and address software vulnerabilities. Three primary approaches are commonly employed. Black box testing. Imagine trying to crack a safe without knowing the combination or its inner workings. Black box testing simulates this scenario. Testers have no prior knowledge of the application's internal structure or code. They interact with the software as a user would, attempting to identify vulnerabilities through trial and error. White box testing. In contrast, white box testing is like having the safe's blueprints in combination. Testers have full access to the application's source code, design documents, and other internal information. This allows for more comprehensive testing, as they can examine the code directly to identify potential weaknesses. Gray box testing. As the name suggests, gray box testing falls between black box and white box testing. Testers have partial knowledge of the application's internals, such as access to certain system architectures or data flow diagrams. This approach strikes a balance between the two extremes, allowing for more targeted testing while still maintaining some level of independence. The choice of which approach to use depends on various factors, such as the application's complexity, the testing goals, and the available resources. Often, a combination of these approaches is employed to provide a more comprehensive assessment of an application's security posture. Section 5. Advanced Arsenal. Deep dive into modern vulnerability testing techniques. As software development practices evolve and cyber threats become more sophisticated, new vulnerability testing techniques have emerged to address the changing landscape. Let's explore some of these advanced methods. Static Application Security Testing, or SAST, is like a meticulous code review conducted by automated tools. SAST tools scan an application's source code, bytecode, or binary code for potential vulnerabilities. They can identify a wide range of flaws, including injection flaws, cross-site scripting vulnerabilities, and insecure coding practices. Dynamic Application Security Testing, or DAST, on the other hand, analyzes code in its running state. DAST tools act like automated attackers, sending requests to the application and analyzing its responses to identify vulnerabilities. This approach is particularly effective at uncovering runtime vulnerabilities and configuration issues. Interactive Application Security Testing, or IAST, combines the strengths of both SAST and DAST. IAST agents are deployed within the application's runtime environment, allowing them to analyze code execution and data flow in real time. This provides a more comprehensive view of the application's security posture, enabling the detection of vulnerabilities that might be missed by SAST or DAST alone. Software Composition Analysis, or SCA, is crucial for modern applications that rely heavily on open-source components and third-party libraries. SCA tools scan an application's dependencies to identify known vulnerabilities in these external components. This is essential for managing supply chain risks and ensuring that all components of an application are secure. Penetration testing is often considered the gold standard of security testing. It involves simulating real-world attacks to identify vulnerabilities. Ethical hackers, also known as penetration testers, use a combination of manual and automated techniques to attempt to breach an application's defenses. Fuzz testing is like bombarding an application with random or unexpected inputs to see how it reacts. This technique can uncover vulnerabilities that might not be found through other methods, such as buffer overflows, memory leaks, or input validation errors. By employing a combination of these advanced vulnerability testing techniques, organizations can significantly enhance their ability to identify and remediate security weaknesses in their applications. Section 6. A systematic approach, the vulnerability testing lifecycle in action. Effective vulnerability testing is not a one-time event but an ongoing process that should be integrated into the entire software development lifecycle. A systematic approach, often referred to as the vulnerability testing lifecycle, can help organizations establish a structured and repeatable process for identifying and addressing security weaknesses. The lifecycle typically consists of the following phases. 1. Planning and scoping. The first step is to define the scope of the testing engagement. This involves identifying the applications to be tested, the testing objectives, and the resources available. 2. Reconnaissance. Before launching into testing, it's crucial to gather information about the target application. This might involve reviewing documentation, performing network scans, or using open-source intelligence tools. 3. Scanning. This phase involves using automated tools to scan the application for potential vulnerabilities. SAST, DAST, and SCA tools are commonly employed during this phase. 4. Vulnerability assessment. Once potential vulnerabilities have been identified, they need to be assessed for their severity and potential impact. This involves analyzing the vulnerability, understanding its exploitability, and determining the potential consequences of a successful exploit. 5. Remediation. Once vulnerabilities have been assessed, the next step is to remediate them. This might involve fixing code, reconfiguring systems, or applying security patches. 6. Verification and retesting. After remediation, it's essential to verify that the vulnerabilities have been successfully addressed. This typically involves retesting the application to ensure that the vulnerabilities are no longer present. 7. Reporting. The final step is to document the findings of the vulnerability testing engagement. This report should include a summary of the vulnerabilities identified, their severity, and the remediation actions taken. By following a structured vulnerability testing lifecycle, organizations can ensure that their applications are tested thoroughly, and that security weaknesses are identified and addressed in a timely manner. Section 7. Best practices. Fortifying your software against attacks. While employing advanced testing techniques is crucial, it's equally important to establish a robust security foundation throughout the software development process. Here are some best practices to fortify your applications against attacks. Shift left security. Integrating security testing early in the software development lifecycle is essential. By identifying and addressing vulnerabilities during the design and development phases, organizations can prevent costly rework later on. Leveraging OWASP Top 10, the Open Web Application Security Project. Top 10 is a widely recognized list of the most critical web application security risks. Organizations should prioritize addressing these vulnerabilities to mitigate common attack vectors. Secure coding practices. Developers play a critical role in building secure software. By adhering to secure coding practices such as input validation, output encoding, and proper error handling, developers can prevent many common vulnerabilities from ever existing in the codebase. Automating security testing. Automating security testing tasks, such as running SAST and DAST scans, can significantly improve efficiency and reduce the likelihood of human error. This allows security teams to focus on more complex tasks, such as vulnerability analysis and remediation. Continuous monitoring. Security is not a one-time event but an ongoing process. Organizations should implement continuous monitoring solutions to detect and respond to threats in real time. This includes monitoring logs, network traffic, and system events for suspicious activity. By embracing these best practices, organizations can create a security-first culture and build more resilient applications that are better equipped to withstand the ever-evolving threat landscape. Section 8. A cautionary tale. The Log4 Shell Vulnerability and its Impact. The Log4 Shell vulnerability, discovered in late 2021, served as a stark reminder of the potential impact of software vulnerabilities. This critical vulnerability, found in the widely used Log4j logging library, allowed attackers to execute arbitrary code on affected systems. The impact of Log4 Shell was widespread and severe. Organizations worldwide scrambled to patch their systems as attackers actively exploited the vulnerability to gain unauthorized access, steal data, and disrupt services. The incident highlighted the importance of supply chain security. Log4j is an open-source component used in countless applications. The incident underscored the need for organizations to carefully manage their software supply chains and ensure the security of all components, including third-party libraries. Timely patching. Software vendors quickly released patches to address the Log4 Shell vulnerability. However, many organizations were slow to apply these patches, leaving their systems vulnerable to attack. Timely patching is crucial for mitigating the risk of known vulnerabilities. The importance of vulnerability management. Organizations with robust vulnerability management programs were better equipped to respond to the Log4 Shell incident. These programs typically involve regularly scanning for vulnerabilities, prioritizing remediation efforts, and tracking patching progress. The Log4 Shell vulnerability served as a wake-up call for organizations to prioritize software security and implement robust vulnerability management practices. Section 9. Looking ahead. Future trends shaping vulnerability testing. The field of vulnerability testing is constantly evolving, driven by advances in technology and the ever-changing threat landscape. Here are some future trends shaping the future of vulnerability testing. AI-powered security testing. Artificial intelligence and machine learning are poised to revolutionize vulnerability testing. AI-powered tools can automate tedious tasks, identify complex patterns, and prioritize vulnerabilities more effectively. Zero-trust security models. Traditional security models often rely on perimeter defenses, assuming that everything inside the network can be trusted. Zero-trust security models, on the other hand, assume that no user or device can be trusted by default. This approach will require new vulnerability testing methodologies that focus on verifying the security of every access request and transaction. Increased focus on cloud security. As more organizations migrate their applications and data to the cloud, cloud security will become increasingly important. Vulnerability testing in cloud environments presents unique challenges, requiring specialized tools and techniques. The rise of DevSecOps. DevSecOps emphasizes collaboration between development, security, and operations teams throughout the software development lifecycle. This approach aims to integrate security testing seamlessly into the development process, fostering a culture of shared responsibility for security. By embracing these emerging trends and adapting to the evolving threat landscape, organizations can stay ahead of attackers and build more secure software for the future.
Please like, share, and subscribe to my channel for more great content.